My name is Youngda Kim from IBS, and I'm also the co-chair of this conference. Before I open this session, as a local organizer, we heard that there's a natural disaster in Japan, and we heard there was more than 150 lives lost. And so we would like to express our sincere condolences to our Japanese community. And I would like to ask you to pray for Japan for a while. Thank you. We have two speakers in this last session. For the first speaker is the Professor Paul Rangaker. He will summarize this conference and give an overview, outlook for the future. Let's welcome Professor Paul Rangaker with a big applause.
Thank you very much, and I'd like to thank the organizers for the invitation. I was asked to spend part of the time talking about the 50-year development of the Standard Model, so that will be the past. I will then talk about something about the conference itself, that's the present, and then thoughts for the future. Now, first, this was an extremely exciting conference. It covered many different things, and we had over 1,100 participants, more than 800 parallel talks in 16 sessions, 41 plenary talks. Obviously, I'm not going to be able to do justice to a summary, and I'm not really even going to try to give a detailed or complete summary. I will instead just comment on some specific points that I think are especially interesting. So I apologize in advance for all the different topics that I'm not going to be able to cover. It's just not possible. Okay, so first let me talk about the past. Happy birthday, Standard Model. And I'm very happy to do this because my own professional career has paralleled almost exactly in time the development and testing of the Standard Model. Okay, first let me say something about the preludes, what went before, because the Standard Model did not just start from nowhere. Well, some of the highlights are the development of the ideas of gauge invariance from QED, Yang-Mills theory, ideas of renormalization, axiomatic field theory, then the development of the Fermi theory of weak interactions, weak Cabibel mixing, and then the V-A theory. The somewhat in parallel, or the latter part of all those developments was much phenomenological progress in the strong interactions, symmetries, quarks, then the idea of color or scaling, spontaneous symmetry breaking, and then in 1964, the Higgs et al. Mechanism. I must emphasize that the Higgs mechanism and the Braudon-Claire and others who were involved were not thinking about the weak interactions at the time. I don't think anybody was thinking about the weak interactions at the time, but it was much more vain, perhaps some hope of applying to strong interaction symmetries. The actual birth is usually given as 1967, when Weinberg wrote down his theory of leptons, and then Salam a similar theory the following year. And developments soon thereafter in parallel were the GEM mechanism, the actual prediction and discovery of the charm quark, the third family, and CP violation. By the way, the third family, of course, was not part of the original Standard Model. The Standard Model has grown in scope over the years, and I think that's appropriate. The weak neutral current in 1973 and the W and Z in 1983 were the key experimental inputs that really solidified the SU2 cross U1 model. Renormalizability was proven in 1971. And here is the Standard Model Lagrangian written in a non-compact form. And there's a sign error there, and anybody who can find a sign error, let me know. We went through many types of precision experiments of the electroweak theory, and especially starting around 1989 at the start of the LEP and then SOC era. The flavor physics, the unitarity triangle, and the associated things was the other big underpinning of the SU2 cross U1 model. The neutrino mass and mixing, first of all, I am going to define the Standard Model to include neutrino mass. Some people don't, but I think it should be added in just as the third family was. We still don't know whether the masses are Dirac or Majorana, but we do know that there's mass and mixing. By the way, those of us who worked in neutrino physics were pretty much convinced from the Davis experiment and from the Kamiokande and the earlier super Kamiokande results that there was neutrino mass. It was 98 was only the sort of the clinching time when the evidence was definitive. And then the Higgs or BEH boson, announced in 2012, is usually considered as the final step, the final ingredient, although of course we still don't know the details of the neutrino mass. QCD is part of the Standard Model as well, and this was developed in parallel. First of all, it was deep inelastic scattering, and then E plus E minus annihilation that gradually developed or verified the ideas of quarks and partons and color. The ideas of asymptotic freedom, infrared slavery, confinement were developed around the same time as the early part of the electroweak model. And then the gluon was observed experimentally at DAISY. And then the whole apparatus of perturbative QCD, jets, hadronization, generators, et cetera, came about. And then I want to also mention lattice QCD as an integral part of the theoretical underpinning of the QCD. The Standard Model has many successes. It describes ordinary matter and interactions down to a level of about 1,000th the size of the atomic nucleus. This is an incredible feat. When I first entered graduate school, I don't think anybody thought that we would understand the weak or the strong interactions in our lifetimes, but it all fell in place. The theory is mathematically consistent. It makes many, many predictions and tests that we've heard about the latest aspects of at this conference. And it incorporates, it's very important to mention, some of the symmetries of nature that are at least accidental symmetries, approximate symmetries such as baryon and lepton number are automatic in the Standard Model in that you cannot write down renormalizable terms that would violate them. And there are, however, all the well-known problems that I won't go through in detail. It's very complicated, lots of parameters. The fermion spectrum is very complicated. There's the notorious fine-tunings. There's the issue of incorporating quantum gravity, initial conditions on the Big Bang. Where does the baryon asymmetry come from? Dark matter and energy. And then towards the end, I'll say something about the paradigms that underlie not only the Standard Model, but particle physics in general. Okay, now that was the past. Now let's turn to the present. and some comments on aspects of things that occurred in this conference, and would focus on the last 2 years since the previous one. I guess the biggest thing to me is not any particular discovery that was announced, but rather the enormous technical advances on all fronts that I'm sure will pay great dividends in the future. The LHC luminosity, it's twice the design luminosity. It's working great. The disadvantage of luminosity is enormous pile-up, and I have great admiration for the experimenters for dealing with that. The detector upgrades, everything in analysis of new physics, machine learning, the theoretical efforts in perturbative QCD, the PDFs, jet substructure, generators, amplitude methods, lattice calculations, all enormously impressive. And this is not just hadron colliders, it's the field in general. Just a couple plots of some of the standard tests of the standard model. Of course, you can't read or absorb all the details, but we know that so many things have been measured at the LHC and in wonderful agreement with the standard model. One new thing is that Bell 2 has started running at Super KEKB this year, and it has the luminosity is or will be 40 times that of KEK, and this apparently is working very well, and so we're also expecting a lot from this. Okay, now some highlights of the actual physics. Of course, the Higgs is something that's very central to our field now. And is it the standard model Higgs? I mean, there's lots of possibilities. There may be just more complicated Higgs structures. Perhaps the Higgs is really some sort of composite. Well, we've had presented much more precise data on the mass and couplings from the CMS and ATLAS. We now have perhaps the experimental highlight. Here is the TTH production mode has been measured at more than 6 sigma, and BB bar and tau plus tau minus are now established at more than the 5 sigma. In fact, all the major production modes have now been established, and distributions such as PT distributions, a lot of limits on additional extended Higgs sectors. And here are some more plots. Here's the famous plot of mass versus coupling to the Higgs, a CMS display of a TTH event, etc. In fact, all of the major production and decay modes have now been observed. However, in order to probe these various extensions, one will often want to have much more precision than we already have, perhaps down at the percent level or better. And this is, at some level, we'll get more information this run and in run 3, but for the future, we really need a high luminosity LHC, and we need future facilities to really get the precision down to where we would like it to be. One of the goals is to measure the cubic Higgs vertex, which is induced in the standard model by symmetry breaking. It's not there to begin with, and that's especially sensitive to new physics. But that's something for the future. Similarly, a direct measurement of the total width via E plus E minus goes to Z Higgs is something for the future. Okay, we've heard talks this morning about the heavy ion program. This is something I didn't know a lot about, frankly, previously, but I'm very impressed by both the technology and the physics that has been done, first at RIC and now at LHC. This is very important because it's a basic probe of the structure of QCD, of the phase diagram. It's relevant to the early universe cosmology and to certain dense astrophysical systems. There's now new results on xenon-xenon, for example, in addition to the lead-lead and proton-lead and proton-proton. Characterizations are first that, of course, the system is very hot. It has huge numbers of charged particles. One observes the jet and charm quenching as the hard products of the hard collision propagate through the quark gluon, I'll call it plasma for the moment. But in fact, the azimuthal flows and the long-range correlations are pointing to some sort of collective behavior that's indicative of the fact that we're not really in a ideal gas regime, but it's more like a liquid, almost a perfect fluid or smoothly flowing fluid. And this is something that at least I believe was a surprise, not recent surprise, but from these experiments. So we're starting to really understand the dynamics of what's going on in at least some corner of the temperature versus baryon density phase space. A lot of results on electroweak and top, and I'm not going to make any attempt to really summarize them. There's a very nice new measurement of the effective weak angle in coupling to leptons from the asymmetries at the LHC, which is competitive with the LEP-SLD numbers, but of course is important because the precise LEP-SLD numbers actually involve some rather high and low values from LEP and SLD, which has never been understood. There is production of W and WZ sensitive to triple gauge vertices and new physics therein, and some first indications of WZ scattering, which tests unitarity and electroweak symmetry breaking mechanisms. And very precise measurements of the top mass, which are important for various reasons, such as the stability of the vacuum in the electroweak theory, if the standard model really extends to high energies, and many properties of the top have been or are being measured: cross sections, spin correlations, searches for flavor changing effects, etc. And it was emphasized in a theory talk this morning that the tops are everywhere, enormous numbers at the LHC, and that the theory for the interpretation of the experiments must catch up or must match the experiments. That's true not just for top physics, but for the entire program of precision particle physics. Many exotic searches from the LHC. Perhaps I'll single out vector fermions, that is, new fermions that are not parity violating, in which the left and right have the same SU2 properties, both singlets or both doublets. And these are expected in many extensions of the standard model. Searches for resonances, such as Z primes or W primes or colorons, or possibly light resonances, weakly coupled, long-lived particles, leptoquarks, suggested by the B anomalies. I didn't hear anything about diquarks, but that's another possibility. Hidden dark sectors and portals to them, weak coupling to them. and I actually think that it's a good chance that new physics will show up in one of these surprising ways that is not necessarily something direct like supersymmetry. Unfortunately, they're so ubiquitous in extensions of the standard model that one can turn that around and say that if one observes them, one doesn't immediately know what they're pointing to, whether it's composite Higgs theories or remnants from superstring theories. So many of the high mass resonance searches are in the like 5 TeV range. They're direct searches for leptoquarks. We heard that there are new techniques such as associated production searches, which allow extension to much lighter Z primes with weak coupling that one couldn't get by a direct resonance search. There's also a lot of work, not just here, but generally on jet substructure and boosted jets and the things that you can do with that. Supersymmetry, of course, is motivated by the Higgs naturalness question, gauge unification. It's a WIMP candidate. Coleman-Mandula theorem, that's the theorem that under plausible assumptions that supersymmetry is really the only extension, space-time extension of the Poincare symmetry possible. And of course, string theories and supergravity theories predict supersymmetry, although admittedly in this case, the breaking scale could be anywhere, not necessarily in reach. There are many, many versions of supersymmetry depending on the breaking and mediation of the breaking mechanism. Early searches concentrated on sort of the simple cases of having lots of missing energy and relatively straightforward decays of the squarks and gluinos. But of course, one hasn't observed any of these things, and so it's currently most of the searches that we heard about at this meeting are concentrating on the more difficult cases. Instead of simplified models, the full phenomenological MSSM, which allows for more complicated decays and smaller branching ratios and so forth, and ideas such as compressed stealth, R parity violation, split supersymmetry, light gravitino, and many of which have suppressed missing energy, for example, and a lot of search for electroweak processes and thirds families effects. In Strandberg's summary talk, she emphasized that the limits now are typically 1.5 or 2 TeV for colored objects in the simple cases, but perhaps half or a third of that in these more challenging scenarios, etc. Certainly the limits on supersymmetry are challenging to naturalness ideas, but I think there's still quite a bit of room to go. On the plus side, the fact that if there is supersymmetry, the scale is heavier, that actually relaxes a lot of the constraints that one had from flavor-changing neutral currents, electric dipole moments, Higgs mass. But on the other hand, it makes it much harder to account for something like an anomalous muon magnetic moment. I want to emphasize that supersymmetry is not just the MSSM, that it's very possible or even likely that supersymmetry would be accompanied by, say, additional gauge groups or additional scalars or other things. So one should keep an open mind. Flavor physics is a very big subject. There's an enormous amount of work on the CKM matrix and CP violation, which I'm not going to make any attempt to summarize here. One highlight is the nagging VCB puzzle has been resolved. That is, for years, the determinations of VCB from exclusive decays and from inclusive decays disagreed, but now this has been resolved by a new Bell analysis that basically uses much more data-driven inputs to form factors. There's still a problem with the with VUB, and so we're waiting on that one. We have a new, more precise measurement of gamma or 5.3 from LHCb and all kinds of other results, which I'm not going to try to go into. We, of course, all know about the flavor anomalies, the decay of B into D star and tau nu or light lepton pair goes according to tree level exchange of a W boson, and this exchange should be identical for the tau and mu up to relative up to mass effects, but the actual measurements are large. If this is a real effect and not some kind of fluctuation, then it could be accounted for, say, by a leptoquark exchange. And but this is somewhat remarkable because the standard model matrix element is large in some sense. So a big deviation, it's a big deviation on something that's large or normal size to begin with. However, I mean, there certainly is room for leptoquark, and if there is one, you can look for it in direct production, and there are CMS is somewhat closing in on direct production limits. There's anomaly also in the B goes to K star mu versus B in B goes to K mu over B to KEE, or a corresponding thing with the K star. Now this is a strongly suppressed decays in the standard model and going by a penguin. So these are very small in the standard model, so new physics effect might be expected to show up more strongly. Again, a tree-level leptoquark exchange or a Z prime could account for it if it's real. Diagram something like this with a Z prime. It wouldn't have to be a penguin. It could be just some flavor-changing vertex. There are also some indications in the angular distribution of a problem, although that's still not as precise as one. Well, it will get more precise, let's put it that way. And so we're anxiously awaiting for the data from LHCb in run 2 and the data from Bell 2, which should be able to explore these effects in much more detail. Again, there is, say in the Z prime model, there is certainly parameter regions that are not excluded by other tests. There are many, many other flavor type things that I'm not going to have time to talk about in the bottom and charm system and CP violation, flavor changing effects in the lepton sector, and in the kaon decays, and electric dipole moments, and some possible deviations in the proton radius from the muonic atom Lamshift, and discrepancies in neutron lifetime measurements, possible problem with epsilon prime over epsilon. So there's a whole array of other important flavor physics to investigate. I'll say relatively little about strong interactions, which was talked about this morning. There was a very nice talk on the lattice QCD, which is really impressed me enormously for years how successful it was, but now, as we heard this morning, it's shedding light on all kinds of matrix elements and properties where strong interactions are relevant. There's a lot of work that I couldn't begin to summarize in detail about exotic hadrons, that is, 4-quark or 5-quark systems, which could be loosely coupled molecules, say, of two mesons, or they could be strongly coupled systems consisting of a diquark and an anti-diquark, or other possibilities. And so mapping out the spectroscopy and trying to determine the character. There was a very interesting talk this morning on generalized parton distributions as probed, for example, in electron scattering, and how these provide basically three-dimensional maps of the structure of the proton, and even of things like the pressure distributions inside of it. Neutrino physics. Well, neutrinos have always been an interesting probe of particle physics, astrophysics, and cosmology simultaneously. You have to unravel the things there. Some of the highlights that are relatively new is the double show now has a theta 1-3 that is confirming the earlier results from Diabé and Reno. The new results from T2K and NOVA. NOVA has its first anti-neutrino run presented. The normal hierarchy, this one seems, this is the normal hierarchy. No, I should have looked at the, yeah, this is the normal hierarchy in which the one state is much heavier than the other two, is weakly favored. It's certainly not definitive yet, but there's starting to be some indication of that. There's some indication of CP violation of the CP phase in the PMNS matrix, with a phase that is perhaps around minus, minus 2 pi. Again, not definitive, but it's suggestive. The NOVA experiment has fairly strong indications that the theta 2-3, the mixing relative to atmospheric neutrinos is not maximal, but rather that it's offset and in the upper quadrant. The other experiments are all still consistent with maximal. So that is a very important result. We still don't know Majorana or Dirac. Majorana, of course, would suggest some sort of seesaw model and would connect to leptogenesis. However, new symmetries could certainly restrict the Yukawa couplings and allow for Dirac neutrinos. Mixing patterns could be due to perturbations on some tri-bimaximal mixing, and in the theory talk, that was argued very strongly. In fact, in my view, that just as plausible are other possibilities, such as a so-called anarchic pattern that would be probably more likely from a superstring point of view. There's an active short baseline program at Fermilab with Microboon running and the two other liquid argon detectors coming online, which will, amongst other things, probe the cross sections. And of course, a very interesting coherent elastic neutrino nucleus scattering from coherent at Oak Ridge. Katrine has finally started running. It's a beta decay endpoint, tritium beta decay endpoint experiment, hoping to get down in sensitivity to an effective mass of about 0.2 electron volts. Neutrinoless double beta decay experiments, there's a number of them. This is a plot of the lightest of the neutrinos and the effective mass that enters the formulae, and we should be able to eventually, with the planned experiments, to probe the inverted hierarchy region. It's unlikely that we'll be able to get down in the near future to the normal hierarchy region. I forgot to put on the slide that there's always the issue of the nuclear matrix elements in interpreting these limits. There's a whole array of other neutrino topics that I won't go into. Is there a sterile neutrino? The new mini-Boone results are now claimed to be consistent with LSND. This is their spectrum of events in the, that they're observing in neutrino and anti-neutrino. And there is still an excess of events at very low energy that is frankly not fit very well, even with the neutrino oscillation hypothesis. So we have to really wait for microboom to clean this up. But there are indications here. The reactor anomaly, the deficit in neutrinos in the reactor, which had been suggested as indicating sterile neutrinos, the case is weakened by the Diabé and Reno analyses, which by timing the fuel cycles can separate out the flux of U-235 and P-239 neutrinos. And it seems like the deficit is in the U-235 and not the P-239, whereas a sterile interpretation would expect them to both be reduced similarly. There are an array of new very short baseline experiments that do not depend on the actual detailed calculation of the prediction of the flux and other source experiments, and so we should get and some of these are running now, and we should get a real answer to this within a year or two. There's also the famous conflict with the disappearance of muon neutrinos, which seems to conflict with the sterile neutrino idea. Altogether, there's no coherent picture that one can put together at present, at least within the neutrino context. I should also add that sterile neutrinos would conflict with standard cosmological constraints unless one modifies somehow the cosmology or to get around that. And I'll also mention that active sterile neutrino mixing is difficult theoretically because you need to have small Dirac masses and small Majorana masses simultaneously, two different things. Anyway, this should be resolved within a couple of years. Dark matter, many candidates. We just heard a talk on this. The modifications of Newtonian dynamics seem to not really work on large scales or for the bullet cluster. There's many candidates. I won't go through all this. There is a very active program of direct searches, indirect searches, collider searches. There is unexplained DAMA results, which are rather compelling statistically, but which are in clear contradiction with other experiments within the canonical dark matter interpretation. I won't go through the details. Here's the canonical plots of the spin independent, the limits of WIMP mass versus cross section for spin independent and spin dependent scattering, and we're almost at the neutrino background floor. That is the background just from solar and atmospheric neutrinos. Also, very active program at the LHC. Searching for monojets or other single particles along with dark matter. And there's indirect searches, one of which I'll mention later. A lot of progress on the axion searches and the one experiment is actually now down probing into the window of axion cold dark matter which could also solve strong CP problem. And so this region that's relevant to axions and strong CP should be settled, either a discovery or that region ruled out. And there are other experiments underway, such as active program here in Korea. I'll say very little about cosmic rays. I obviously have to be very brief about the things that happened in the last session. But we heard that there are now a number of satellites looking in the up to 10 TeV for electrons, positrons, protons, antiprotons, and of course this is the overall cosmic ray spectrum. And as we just heard, we have a very dramatic new AMS result of the positron spectrum, and we clearly see that it keeps going up until about 300 GeV and then turns over. And although it's possible that this has something to do with cosmic ray propagation or pulsars or something, those are difficult, and some sort of TeV decaying dark matter might be a natural explanation. Similarly with the anti-proton spectrum. I want to mention that IceCube has two candidates for tau neutrinos, high energy tau neutrinos. That's very interesting because they didn't before. If the high energy neutrinos are due to pion decay ultimately, then they started out with 1 electron, 2 muon, and 0 tau neutrinos. And by the time they get to us, there should be a 1-to-1-to-1 ratio. And with these two events, if they hold up, that would be consistent with this ratio. They've also observed one event that is consistent with the so-called Glashow resonance, which has been long awaited. That's high energy antineutrino scattering from an electron in the atmosphere to produce a W boson. Gravity waves, one of the most exciting things in the, at least peripheral to our field, and in particular the neutron-star merger event. This and the black hole mergers probe general relativity and astrophysics, and maybe a standard siren. They are a site of the, pretty much settles the issue of the site of the R process. That is, the R process is a rapid neutron absorption process to create very heavy nuclei, and it's been for decades. The question is, where in astrophysics does it occur? And the favorite candidate used to be supernova explosions, but apparently most of them come from these neutron-star mergers. The speed of the gravity wave is almost identical to light speed, and that excludes many dark energy models. And in the far future, when we have things like satellites measuring gravity waves, there will be probes of things that are of very direct relevance to particle physics. Lots and lots of other important topics have been discussed at this meeting, and I just don't have time for them. Okay. Now let me go to the third part, the future. Okay, I want to first of all emphasize that from Newton's law of gravitation to Einstein's general relativity took 230 years. Newtonian gravity survived precisely for 230 years, or 175 if you want to count the observation of the precession of Mercury's perihelion. I emphasize this because we often get a lot of disappointment in our field because it's been around for 50 years and it's now been sort of established 6 years ago, and we get very impatient that we'd love to see something new. Well, from some point of view, it wouldn't be such a great theory, wouldn't be such a great triumph if it had fallen apart right after discovery. Now, of course, I'm well aware of the fact that we're humans and we need to get funding, we need to get jobs, we want to have interesting things to work on, and so obviously we don't want to wait for 230 years for something new, but nevertheless, I think you should keep that perspective that it's more of a success if it doesn't fall apart right away. In parallel with the standard model, the standard cosmological model was developed. What's the next step? When will we find something new? What will be the time scale? And what will be its nature? I don't know what its nature will be, but I suspect that one possibility is that we mainly talk about is that there will be new layers of matter or interactions at the TeV scale or 10 TeV scale. There are other possibilities that I'll come to at the end that I'll call the new standard model of nature. That's is my dream of a true standard model that works all the way up to the Planck scale and incorporates cosmology, but that's just a dream. At any rate, the developments, the progress is not going to come from people like me, but it's going to come from people like this, young people. Okay, the standard model, I showed this slide before. I'm just repeating its successes and problems and missing ingredients and questions. And there are, in addition to the things missing, there are the possible anomalies, and there are much of our effort is searching for beyond the standard model. And so I'm going to talk a little about conventional ideas and about non-conventional things. Okay, there are not that many different classes of ideas of what might lie beyond the standard model. Some of the more conventional ones are new symmetries or compositeness, large or warped extra dimensions, dark or hidden sectors, some sort of unification in a grand unified theory or a superstring theory, new dynamical ideas, go by names like relaxion or clockwork theories, or string instantons is a completely different class. That's a possibility of exponentially suppressed non-perturbative effects in string theory. Random or environmental selection goes under the name multiverse. String remnants, and I'll say something about that because that's something that I'm very interested in. String remnants are things that might occur in a string theory in its compactification to 4 dimensions that don't solve any problem. They just happen to be there, slip through the nets when the string theory is compactified. These are very, very common and of fairly specific types. Or here be dragons. There could be things that are totally different, emergent dimensions or interactions, hidden variable theories that somehow evade existing constraints. Okay, now let me spend a few minutes examining some of the paradigms under which we work, because I think it's very important at this stage, given the fact that we are not seeing immediately new physics at the TeV scale. One of the paradigms or things to keep in mind is that within the normal field theory playground that most phenomenologists work in, and most experimenters think about it exploring, there's really an infinite landscape of possible field theories, an infinite number of possibilities, and it's continuum, in fact, given. And we haven't a clue as to what the selection principle is, why one of them happens to be our world. people often will invoke ideas like minimality or naturalness or elegance or, quote, uniqueness, unquote. By uniqueness, I mean you make a bunch of assumptions, and with all those extra assumptions, things are unique. The other issue is nature seems to be just right. That is, the dark energy is tiny compared to what one would expect from any kind of naturalness argument, even compared to the electroweak scale or a string scale. And it has to be small, or there wouldn't be any galaxies. If it were too big, the universe would expand so fast there'd never be time for anything to form, or if it were negative, it would collapse so fast. And the interactions and parameters, et cetera, are such that rather delicately tuned, actually, to allow a huge variety of stable atoms, stars, et cetera, that are certainly necessary for life as we know it. Or another example, if we did not have 3 large dimensions of space, there wouldn't be any stable orbits, planetary orbits. So one doesn't usually think about these questions. What selects the theory, and why is it so convenient? Why is it such a nice theory, so comfortable for our existence? And they must be explained simultaneously. Minimality is often invoked. Occam's razor is often a good guide, but it's not always a good guide. The DNA molecule is very much more complicated than it seems to need to be, as is the human brain, as is the standard model. And I won't explain these, but for those who know what these pictures are, sometimes the minimal solution is not the right solution. I already mentioned remnants. These are accidental low-energy features of an ultraviolet theory which slip through the cracks and are just there. If you've got a high-scale theory and much of the stuff is broken, gets a high-scale mass, sometimes light stuff just survives by accident and might not solve any problem of the standard model. That's what I mean by remnants. And the most familiar types are the moduli or axions from string theories, Z-primes, larger Higgs sectors, vector pairs of fermions, hidden sectors, etc. Naturalness or tuning. The Higgs mass squared is very unnatural, unless there's some the physics that we're all looking for. But so far, we haven't seen signs of those types of new physics. And so perhaps naturalness has been a wonderful guide in the past. There's some famous examples of things that were predicted or could have been predicted from naturalness ideas, but it seems to fail totally for the dark energy. And in fact, I think the most promising solution to the dark energy problem is the environmental solution, which may in fact be a consequence of a string theory with a landscape of vacua and some form of eternal inflation to sample all those vacua. I'll explain a little more what I mean by environmental solution. But of course, the big problem in this sort of thing is falsification or verification. There are other very clever dynamical schemes as well that are at least technically natural. Uniqueness or environment. Well, uniqueness, again, this is the assumption that there's some simple, unique underlying theory, even though we don't know what the selection principle is. And gauge theories seem to be somewhat unique, although you have to specify the group representations, et cetera, et cetera. But the Yukawa sector of the standard model seems unconstrained unless one adds new symmetries or principles. But then I always like to come back to this famous historical example, Kepler. He spent much of his early years trying to understand the ratios of the radii of the known planetary orbits. And he found a good, fairly successful, very successful with the accuracy at the time, solution, assuming that the orbits corresponded to stacking all of the basic platonic solids in each other, and that gave actually a good prediction or post-diction for the orbits. But we know that that was the wrong paradigm. There's no simple symmetry argument that explains the orbits. It depends, there's lots of solar systems, and it just depends on their origin. Similarly, people at some point in the past, some people asked, well, why are we so lucky that we have the right temperature for liquid water and life can develop here? Well, again, the answer is it's not a mystery. There's lots of planets, and life develops where it's suitable. Okay, the environmental paradigm is analogous to the planets. It's that there may be no simple explanation of some parameters. There may, in string theory, there seems to be an enormous number of possible vacua, one underlying theory, but many, 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 many solutions with no known selection principle. And these correspond to different physics. Most are not suitable for life. Some are. Most of them won't have any stars or galaxies or anything, but a very few that happen to be right will be. And this is this multiverse of possible universes may be actually sampled by some form of inflation in which many universes keep spinning off of each other, and some of them will be just right for life, and the vast majority will not be. This is, in this case, some parameters might be essentially random, and some might be environmentally selected. That is, we wouldn't be here if they were wrong. This is known as the terrible anthropic principle. I used to think that that was a crazy tautology, but if you have something like a string theory with multiple vacua and something like inflation, which can sample all of these, then I think you have to take it seriously. Okay, now the question, however, is this idea of the string theory and multiverse falsifiable, testable, believable, desirable, true, scientific. And lots of people out there say no, 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 no to all of these things, but I think that there's a lot of prejudice there, and I think the idea should be taken more seriously. Okay, first of all, string theory is apparently a consistent and finite theory of quantum gravity, at least perturbatively. That's not a small accomplishment. People struggled for decades and decades with this problem, and it's been solved. String theory does it. This multiverse environmental idea may follow from string theory, eternal inflation. We don't know if string theory is right or eternal inflation is right, but these are things that can be worked on. There is the swampland conjecture that's been very popular in the string community recently. It's more than a conjecture. It's experience based on examining all kinds of compactifications. And this conjecture is that most of the otherwise consistent effective field theories that are probably not found in the landscape of string theory or of any other quantum gravity. This is technically a conjecture, but it's a lot of empirical evidence from it. Some simple examples are large representations virtually never occur in string compactifications, like 126-dimensional Higgs representations invoked in some neutrino mass theories, global symmetries, trifundamentals, representations, etc. These remnants are perhaps the best possibility for getting evidence for an underlying string theory, unless that string theory just happened to have a very low string scale. And that's, in some sense, my biggest hope in the particle frontier for actually observing directly the results of these things. If they were observed, it would be hard, but perhaps not impossible to distinguish from other sources. Technical progress on the understanding of string theory and inflation, both on the theoretical front and observational front for inflation is certainly possible. For example, a big debate in the string community is whether these 10 to the 100,000 vacuum, how many of them are really metastable or de Sitter, that is positive cosmological constant. And that's an issue that will be settled theoretically. It may turn out that I think it is possible that the whole picture I described could be falsified, that the vacuum are not suitable. There may be completely new ideas. Before the observation of the CMB by Penzias and Wilson, nobody dreamt of the precision of the CMB for cosmology. 20 years ago, I don't think anybody dreamt of what DNA could do for paleoanthropology. There may be new ideas. At any rate, I think one should take these ideas very seriously. I'm not saying they're true, but they should be taken much more seriously than they are. This multiverse would be the sixth Copernican revolution. We've had 5 others. The sun doesn't go around us. The galaxy, we're not at the center of the galaxy. There's other planetary systems in the galaxy. There are other galaxies, and our matter is only a small fraction of all the matter. Okay, so there are all these ideas in the last couple of minutes, and how will we make progress? Well, LHC program's been spectacular, and on all technical fronts, and I'm including theory, experiment, accelerator, people, model of international collaboration, and it's been fantastic. And well, we've all seen the projections for the future for the next 20 years or so. We have possibilities, and 5 years ago, there didn't seem to be much planned beyond that, but now it's very serious plans for order 100 TeV, PP colliders, and other possibilities, although there's no no-lose theorem for the physics of these things. Heavy ion program, I think, is very encouraging, and then there's new technologies that are being developed, and machine learning, which is also, by the way, starting to be applied to studying the string landscape. Precision frontier, we have on a shorter time scale, proposed E plus E minus programs to probe the Higgs couplings and redo the Z-pole physics. The LHCb and Bell 2 especially, physics programs, plus the things like the Flavor changing neutral currents in the muon magnetic moment, proton decay experiments at hyper K and Dune, and then searches for weak, light, dark, or long-lived particles, even in atomic molecular optical tests of effects on atomic energy levels. Just incredibly impressive stuff. Every time I hear talks on all this stuff, it's just mind-boggling. On the neutrino front, I won't elaborate because I'm basically out of time, but there's a big program ahead that, on many fronts. The cosmology and astrophysics, active program, investigate dark matter, and CMB, and baryonic acoustic oscillations and dark energy, gravity wave, high energy cosmic rays, for probing inflation, dark matter and energy, neutrino properties, possibly moduli from string theory, phase transitions. Here we have, I'll mention this discrepancy we heard about in the Hubble parameter that needs to be resolved. The realities are, however, we live in a political world where there are political, economic, and human resource realities, which are a major challenge to all of these programs. Outreach is essential. Here, spin-off technology, of course, is very important, although I don't think one should rely on it too much. I think we need to emphasize that high-energy physics is really a model for international cooperation. Finally, the quest. This is my dream for the future, to have a new standard model of nature valid up to the Planck scale, the universe on the largest scale in earliest time, or at least as far as we can go. To achieve this would take experimental input. There's got to be stuff that we can measure at low energy, and we need bottom-up theory to work upwards. We need top-down theory. We need ingenuity, hard work, and luck, and of course the cooperation of nature. And I have no idea if, we'll achieve this in the next 10 or 20 or 30 or 500 or 1,000 years, but I think we should try. It'd be such an achievement. Okay, that's it. I just want to thank again everybody for a wonderful conference. That's it.
Thank you, Paul, for thorough, complete review and conference and very insight outlook for the future. Do you have some questions, comments? I don't see. So if not, let's thank Paul again for. And the last speaker of this conference, we call him the man of invisible action. Now I think he has another name, the man of ICHEF 2018. Let's welcome the Professor Ginny Kim for his also concluding remarks.
Well, I am asked to wrap up this conference. This title was given by the program committee. Maybe wrap up for this conference, but I will wrap up ICHEF 70 years. So the statistics was shown by Heidi Hellman yesterday, so I just mentioned the total number of participants was close to 1,200. I read John Polkinghorne's Rochester Roundabout. That discussed until 20th ICHEF. So it started after wartime. Wartime, it was a Manhattan project, and the first Shelter Island conference was June 1. And 25 people gathered there, including Lam and other people. And the second Shelter Island was Pocono Mountains. And Oppenheimer declared there, it is our problem to solve the problem of infinity. That problem of infinity was raised by Lam Shift a year earlier. Then, 1949, there was a third Shelter Island somewhere in Hudson River. Those three were organized by Robert Oppenheimer. Then Marshak continue this series conference from 1950, December 16. That was the first Rochester conference. So far, this ECHAP was helped by CERN and the Fermi Lab. These were two world labs affecting most ECHAPs. Hope that in the future, Asian labs rise up to this stage. Next. So 21st ECHAP was in Paris. That is the beginning of dark age above 100 GeV. I remember that IMB reported that there is no proton decay. We remember from this time, we were in chaos. So somehow, after that, superstring came and most theories work in superstring theory. But I remember 1986 in Berkeley, Weinberg in the closing talk demonstrate MSW effect. And most physicists started working on MSW effect after 1986 ECHAP. So all important discoveries were reported at ECHAP. Next. 39th Seoul, we have 38 plenary talks. 16th, sorry. 16th was the Chicago, and there were 18 plenary talks. And in 16, I want to show you this transparency. They classified by two, strong interaction and weak interaction. We remember this story. That's famous people gave this talk, weak interactions, and Benny talked about weak interactions. So, in 2018 ECHAP, we confirmed that both of them, these weak interactions and strong interactions discussed there, are based on Gauge principle. Now we believe Gauge principle. So here we talked about how successful the standard model is. You all heard about that. And current dilemma is there is no guidelines. There is no guidelines. We could not invite a plenary speaker for BSM theory for the future. And the organizing committee, local organizing committee and the international other IAC tried to have BSM speaker. But maybe we need not this BSM speaker because in every section there is a BSM talk. But this BSM we want to have was basically based on unification theme and gauge hierarchy problem. So maybe, I don't know, in the future each FED they will have this one, but we are in chaos. Maybe this hierarchy problem may not be in the future. So let's remember that 1967 was the beginning of the standard model. From this year, 2018, we begin next second 50 years. So next. In 1972, Gauge principle was advocated. We know that in 1971, we knew this new gauge theory, normalizable gauge theory, and 72 was the beginning. That was Chicago. Now we may need some kind, another kind of such a thing, a unification principle of all forces, including gravity. Next. So we plan to publish the proceedings of science. This will be written at the homepage, and the current idea is 1 hour talk, 20 pages, plenary 10 pages, parallel 6 or 4 pages, poster 2 pages. These include cover page, and we expect the deadline is October 15. Note added should be used, especially for LHC result, for some that you're eager to add in 3 months from now. Conveners and Publication Committee of HF 2018 will compare the text with the slides we have, and will suggest note added if those are not in the slide. Sometimes conference talks are claimed that they discovered something, and we want from 2018 the contents of each proceedings be authentic. For the use in our office, it is not distributed. We plan to make some copies printed as book without the cover page, because there are so many cover pages in Proceedings of Science. So in the first paragraph of introduction, it will be instructed to repeat the abstract in less than 3 pages. And this is the Rochester 2, 1951. You can see Marshall, Oppenheimer, Bethe. It's better to have this kind of record. So I hope previous organizers from 21st until next to help to write this kind of book. And Rochester 11, there was a 7. There was in 1962, I guess. 11th maybe somewhere. So 11th became, from this 7th conference, it was International Conference on High Energy Physics. Before that, it was Rochester Conference. And from that time, every 2 years, it is held. You see many Nobel laureates gathered up, and the place where Higgs boson was announced, there is the same desk as 7. Next. 19th ECHEP, 1978 Tokyo. There, slack polarized electron scattering came a big issue and determined weak mixing angle, basically fixed sin square theta W somewhat the value smaller than we know now. And Paul Langecker gave less thought, and we have fixed that angle to 0.23. And you heard after 20 or 40 years, still this value didn't change very much with the more refined experiment. In this conference, Salam ended his talk. It was not a summary. Some of the ideas I have spoken of up here at this time is simply crazy. Is this idea crazy enough? Citing Bohr. I think you may guess what is this crazy idea is. There was supersymmetry, but this arrow is gone. And I guess that he talked about this crazy idea was supersymmetry, and it was 78. After 78, for last 40 years, many people worked on supersymmetry. After 1980, many people worked, many people from especially 84, and that's about it. And yeah, I think that's what I didn't explain. And the others are our group, our conference became so big. Now there are 38 parallels. And basically, I introduced all these things. And I thank the IBS, especially Center for Action and Precision Physics, Center for Underground Physics, and Center for Theoretical Physics of the Universe, which are IBS centers, who made this conference very successful, and the KPS for hosting these conferences, and the many supporters. I especially thank many important people of local organizing committee, program committee chairman, program committee worked very hard, Youngjun Kwon. Can you stand up? And also Hee Dong-yu, who helped all computer problems working for this indie course. So, Hee Dong-yu. And maybe all this running was run by co-chair Ung Ki-yang, but you know him. Next. Then there was each office quartet. There is you saw them, and Kim So-young, can you stand up? And Kim Ji-nu, 팀장님. 김수아, 양혜리님. When we worked, we didn't know there were some other people, so it was very difficult to see. So I just, they helped us a lot. 신 회장님, 윤은주님, okay, so we'll present some bouquet to them. Can you come up? Yeah. So, let's take it. 가운데로. Thank you. So, each chap 2018 is finished, and next one you will see slides. Next one, so it will be shown here. Can you show?
Come on, let's get ready. You know where we're heading. Giving a jive, living a life. We're gonna hit the heights. When that clock strikes midnight, we don't stop till daylight. So banish your blues, polish your shoes. We're gonna hit the heights. 'Cause I lose my head, feel my body sway when I hear that Creole music start to play. Gotta find that feeling when your mind starts reeling. Ready to blow, raring to go. We're gonna hit the heights. Hit it, boys. If I go real dizzy and I lose control, when I feel that rhythm burning in my soul, I said, come and get it, 'cause you won't regret it. Follow the drum, get out of the slum, we're gonna hit the heights. I said, follow the drum, get out of the slum, head for the neon lights. We're gonna hit the heights. Gonna hit the heights.
Okay, let's see you all in Prague in 2 years. It's a zone.
I agree, my.
Okay, now this conference is adjourned. Okay. See you in 2 years.